Now, if we have an autonomous system of differential equations, all right, so here the unknown function is x, and its value belongs to vector space, right? So in other words, this is rather x of t. So t is a real number and x of t is a vector. But then f of x, the right hand side of the differential equation, is also a vector. So we know that that mappings from Rn to Rn can be visualized as vector fields. Yeah, so by simply we can at each point x, we can plot the corresponding vector f of x, right? So that's familiar stuff from calculus 3. So now for an autonomous system, the direction field it's just simply the right hand side only considered as a vector field, right? So in other words, if we have an example like this, it means that, say, I don't know, say at the point x, y equals, I don't know, pi over 4 times pi over 2, the corresponding vector is going to be cosine of pi over 4 is 1 over root 2 plus sine pi over 2 plus 1, and then sine x, sine pi is 1 over square root 2 minus cosine y is 0. So it means that at this point pi over 4, pi over 2, we would have to plot the vector whose x coordinate is 1 over square root 2 plus 1, and whose y coordinate is 1 over square root 2, and so on. So by doing this on a grid, we construct the whole vector field. Now, again, just as with individual differential equations, there are sort of two styles to plot vector fields. One of them is to plot it in scale. So if the vector has certain norm, then if it is bigger, then we plot it longer. If it is shorter, then we plot it shorter. So that's the first way. Or sometimes it is more convenient to just plot the direction and forget about the length of the vector. So in it really depends. So in this case, in this example, I think it is makes more sense to plot it with scale, because when the picture is with scale, we see the sort of the lines along which the vectors have zero length or very short length. So these are critical lines of the differential equation, and they represent equilibrium solutions, while in the right plot it's not clear, right? It's not, we cannot see them. Sometimes it doesn't matter. So here I think it doesn't really matter. So in either case, we can imagine that equilibrium solutions they live at some certain points, and we can, you know, see them in both versions of the plot, both styles of the plot. And sometimes when these vectors, these arrows, are plotted up to scale, then it's really not convenient, and usually it's the case with linear systems. Right? So with homogeneous linear systems with constant coefficients, believe me, it's always easier to understand the plot if we forget about the length. So we do not do it up to scale and just plot the direction. Okay, so again, this is something familiar. So I hope it's clear. Now, a very important definition. So the phase space of a system of differential equations is the space with coordinates x. So in other words, we forget about t. Right? So if, say, we have one differential equation, right? One variable, one dependent variable. When we forget about t, it's just the straight line. That's all. So if we have a system of two differential equations, so there is t and there is x and y. So we forget about t, and we just take the plane xy, and that's our phase plane. So then a solution of a system is a vector valued function, differentiable on some interval. So the domain of a solution is always an open interval, and then it satisfies the system in the sense that if you substitute it to the system, then we get a true equality. So then a solution of the system can be plotted as a parametric curve in the phase space. So this curve is called a trajectory. Maybe let me emphasize it because it's important. So suppose that let's say we have this differential equation dx dt equals x, right? So its solutions are exponential functions. So x equals e to the t. So that's a solution. So when we plot it on the plane ts, so this is a solution. But now if we want to plot a trajectory, it means that we should forget about t, so that there is no t anymore. So there is just x. So the phase space here is one-dimensional. It's just a phase line x. And then when we plot the parametric curve x equals e to the t, then the only thing that remains here is that if t is increasing, then x is also increasing. So then such parametric curve is going to be straight line and is with just the arrow. So this is the trajectory. Okay. So a phase portrait of an autonomous system is a plot of the phase space with a direction field and some sample of trajectories. So this is a very important notion, and usually we do phase portraits when the system has two dependent variables, two unknowns. So here are a few examples, right? So in the first example we have a familiar differential equation, second order differential equation. So now we are going to convert it to the system of differential equations, right? And then, but notice that at the same time we know that a solution of the system looks like x equals c1 cosine t plus c2 sine t, right? And then y, in our case y is x prime, so y is x prime is going to be minus c1 sine t plus c2 cosine t. So plotting this is the parametric curve that we are going to plot, right? So notice that this is a solution, but if we want to truly plot the graph of a solution, we should plot it in the 3D space rather than in 2D, because we would have three coordinates, so like t, x, y, and the full solution is going to look like a like a spiral. Sorry, in the other direction. So it's a spiral that goes along the t axis. So that's the solution. But when we forget t, the whole solution collapses to plane, and then what we see is this trajectory. Right. So this is a solution, and this is trajectory. Right. But then if we just plot a few trajectories just to kind of to demonstrate what's going on, this is called a phase portrait. So this is a phase portrait of the given system, or equivalently of the given second order differential equation. So here is another example. By the way, as we are going to learn very soon, this is a funny example in the sense that here trajectories, it is impossible to solve the system explicitly. So in the sense that it is impossible to calculate x of t and y of t explicitly, but it is possible to calculate trajectories as an equation on x and y. Alright, so here we can find trajectories, and the behavior here is a bit strange. So what we have is, in the middle we have an equilibrium solution. So equilibrium solution is when or a constant solution, right? So when both x and y are constants, so the derivatives are 0. So to find the equilibrium solution, we can just equate this to 0 and this to 0, and then we can solve for x0 and y0. And what happens here is that all trajectories, they kind of go around the equilibrium. So, and that's what the phase portrait tells us. So that it tells us that there is an equilibrium solution, and that other trajectories, they go around the equilibrium solution. So a slightly modified example. So here again we have an equilibrium solution, but then trajectories of the system, instead of going around the equilibrium solution in cycle, they approach it as in spirals. Okay. Well, and one more complicated behavior that systems of two differential equations may display is called a limit cycle. So here we have a particular trajectory, and other trajectories, they approach this particular trajectory. So the other trajectories will go like this, so and then they just go around this limit cycle, or from the center. So there could be trajectories that approaches this limit cycle, which is why it's called the limit cycle. And the theory of limit cycle is very rich, and we can talk about stable limit cycles, unstable limit cycles, semi-stable limit cycles. But it is quite tricky to prove that a limit cycle exists or does not exist. So we're not going to cover the theory of limit cycles in the lectures, but if you learn it yourselves and apply it to your course project, then you will get a higher score. So now please stop the lecture and try to do the next quiz.